Okay, hello everyone. Welcome to the exercise class 7 for PHYS3041. So I assume that all of you have already seen this exercise problem and had tried your best to work the solution out. Um, but still, let me go through a little bit detail about this question. So a point charge Q is embedded at the center of of a sphere of linear dielectric material with susceptibility chi e and radius r. So here I provide some further hints to you. Is that in linear dielectric material, the electric constant epsilon is actually proportional to the epsilon zero with, with the constant 1 plus chi e. And the polarization P is equals to, again, proportional to the electric field with a constant, again, related to the susceptibility chi e. So I provide this hint as in general, the epsilon and the polarization of a dielectric material could be very complicated. However, fortunately, some of the materials has a linear response with electric field, so we can simplify and approximate these questions with these simple expressions. So let's get started. Let me switch my screen. Okay, so let's get started. So to work out the electric field, all you need to do is really similar with uh, with what you have done before. So here we perform the Gauss law in the dielectric cases. So we work out the D dot dA with the whole surface, and this equals to the enclosed charge. So um, so here D will obviously equals to Q over 4 pi r squared with a normal factor r hat here. So with from the definition of the dielectric field, we can reduce D into electric field E uh, simply by multiplying 1 over epsilon. So here we reached equation 3. So this is the electric field. And then from the hint I provided, uh, like the polarization is actually proportional to the electric field with some constant provided. So this is straight uh, with some straightforward calculation, i.e. just substitute the electric field you've obtained just now, and then you will obtain the polarization P here as shown in equation 4. So with the polarization, we can work out both bond charge density and surface bond charge. So we call that the bond charge density equals to minus divergence of polarization as shown in equation 5. And then we just simply substitute the polarization we obtained just now into this equation, and then we reach to equation 6. Here I factor out this thing into this bracket, as this is uh, relations that you might need to familiar with is divergence of r squared, or sorry, r hat over r squared is actually equals to 4 pi delta function here. So yeah, this is mentioned in the lecture about the vector calculus. So this appears all the times when we describe as point charge density or point distribution here. So then we reach to equation 7. And similarly, with here's a typo here. This should be a normal vector n. However, in the case of spherical, no, uh, in the case of sphere, the normal vector is actually equals to the r hat. So it won't change our result. So the surface bound charge equals to the p dot the normal vector at the surface. So uh, so again, we simply substitute p in equation 8 and evaluate this equation at the surface. That means for r equals to capital R here. So this is the surface bound charge. And then next, we would like to know what is the total surface charge of this configuration. And let me go back one slide. So if you have take a closer look on this surface bound charge, you will notice that this is actually independent of the location, right? As you can see, all quantities here are all constant. That means it is independent of the location. So although usually we need to uh, do some integration to obtain the total surface charge. However, in this case, as it is independent of location, the surface integral can be factored out and then express it as 4 pi r squared, and then we just need to substitute sigma b into equation 10, and then we reach to equation 11. So finally, um, the problem asks um, what is the how can we interpret the location of the surface bound charge? So that means that the negative point where is the negative point charge located? And so let me copy the result we have obtained before as shown at equation 12. You can see that um, this bound charge is actually equals to some charge times the delta function. As I mentioned before, delta function usually used to describe some point charge distribution. So this is obvious that uh, the bound charge is actually can be interpreted as a point charge located at the origin. If this is not intuitive to you, you may do a volume integral on both sides to obtain the total charge you obtain. And you will notice that if you do so, as because of the properties of delta function, you will obtain 0 if your integration does not cover the origin. That means your integral ignored or doesn't cover the point charge. Only when your volume integral cover the origin, then you will obtain the negative charge minus q with an extra constant chi e over 1 plus chi e. So this is obvious that this is a charge distribution of a point charge. Okay, so this is pretty much it. So see you next time. Bye bye.